Welcome back, everybody. Oh, let me get myself organized here. Okay. Any questions concerning the chapters we just completed? I do have one announcement. I just created an announcement on the Canvas course website. What I did was create a PowerPoint presentation listing examples and videos of the different reaction types where actual videos of actual chemicals undergoing. Some of them are pretty undergoing the reaction. Some of them are pretty dramatic. So it's a big file, so you may definitely recommend it to download it rather than watch it online, because it will kind of slow sometimes causes your browser to crash. So PowerPoint slide, it's a PowerPoint slide. If you don't have PowerPoint, remember that Microsoft Office is offered to you free. Go to, I believe, the students. It's one of your. I'll find out where it's at. You can download it if you don't have it. But yes, you can get a copy of it. All right. So no questions. I will continue with the next chapter, which again is a relatively short chapter. This one deals. This is chapter 12, excuse me. Which deals with this concept called a mole. Now, you're all familiar with the term 1 dozen, okay? Obviously, of course. Now, obviously, in 1 dozen, and let me write this down here real quick, is when we talk about 1 dozen, obviously that is 12 items of whatever you're working with, a dozen eggs, a dozen bananas, whatever. It's just a factor. Now, as any factor, much like what we did with respect to the earlier chapter where we did conversions, it's a ratio. And so we can write that ratio one or two ways. So 12 items, here we go again with this ratio, right? It keeps coming back. We can write it in that form with items on the numerator, or we can write it with dozen in the numerator and 12 items in the denominator, okay? Now we're familiar with that, 1 dozen. The mole is nothing more than what we call the chemist dozen. The only problem is, not a problem, is that number just happens to be a lot bigger than 12, okay? And that number is, here we go back to scientific notation, because we're dealing with very large numbers, is 6.02 times 10 to the 23rd. And I'm going to use the term items again, because it is like the term a dozen, it's just 12 items. In this case, it is, again, items, but those items can be molecules, can be ions, it could be bananas, okay? It's just a number. It just happens to be a very, very large number. And that is equal to 1 mole. So a mole is nothing more than a description of a number, just like a dozen is a description of 12, okay? And just like we did with a dozen here, with respect to writing it in the ratio, we can do the same thing with this gigantic number. Okay? Well, this is an old concept, the mole concept. It is fairly old. Here's a scientist who it's named after. It's called Avogadro's number, okay? And like I just stated, we're familiar with a dozen, meaning 12 units. Well, Avogadro's number is 6.02 times 10 to the 23rd. That's a big number. It really is. Take that decimal point on 6.02 and move it over 23 times. And that just gives you an idea as to how big that number is, okay? How big that number is. So that number represents 1 mole. Now, the other aspect about that unit of a mole, that is our common factor that we need when we need to go from chemical A to chemical B in a chemical reaction calculation. The common factor is a mole. I've stated before that we cannot calculate when we say a dozen grams, or excuse me, a gram of reactant A, okay, reacting with whatever number of grams of reactant B. We can't do that calculation until we take grams of reactant A and convert it to moles of reactant A. And then we look at that relationship. Remember that when we were balancing chemical equations, I stated then, remember now, look at the ratio between reactants. Is it a 1-to-1, 2-to-2, 2-to-3, I should say, 4-to-5, whatever ratio that is. We utilize that ratio now to get us to moles of B. Once we're in moles of B, now we can go back to grams, okay? And so it's analogous to, say, fruit. Here's that I got apples and oranges, right? I can't correlate apples and oranges, but if I have a factor that relates the two, which would be the term fruit, then I could correlate the two. I can go from apples to bananas or oranges, whatever. That's what the mole is. So this concept is very important, okay? And it's related to the balanced chemical equations, which I said that ratio is a 1-to-2. Another way to say that is 1 mole of A reacts with 2 moles of B. Okay. All right. So we have Avogadro's number here, humongous number. Okay. So just how big is that number? Okay. It is 602 sextillion. So if you look at here, you look at 1 billion, the 1 billion mark sitting right here. This is 1 billion. 1 with 9 zeros, okay? Avogadro's number is in this realm, in the 6 trillion range. And, give you an idea of, for a Google, for example, that has 100 zeros. And so these are really hefty numbers, okay? Very hefty numbers to give you an idea as to how big this number is. That if you were to count 1, 2, 3, 4, 5, one unit per second, okay, at that rate, it would take you 19 quadrillion years to count that number from 1 to 6.02 times 10 to the 23rd at the end of it. That's how big that is. That is counting at a rate of 1 per second. Okay, so yeah, doing it on a computer, home computer, would just take a long time because it really will put a home computer at well, it's not fast enough to make it happen that quick. So this is just an exercise to allow you to show you how big this number is. I haven't got this number. Okay, so now. When we talk about a mole of anything, another analogy would be if we had a mole of softballs, all those softballs would be the size, all put together, would be the size of the Earth. That's how big they are, okay? But they're extremely tiny. Atoms, when we talk about a mole of atoms, they're very, very, very tiny, okay? And if we had a mole of whatever element we want to look at, we basically have a handful, but keeping in mind that if we had a mole of any of the elements, any of the atoms, we had 6.02 times 10 to the 23rd. In fact, on the periodic table, recall we used the atomic weight. Every element has a different atomic weight, okay? And the units for the atomic weight are, grams per mole, okay? Those are the units for the atomic weight of the elements. Grams per mole, guess what? That is another ratio, okay? Which we can write in both either grams per mole or moles per gram. And knowing these units, it will help us set up the problems correctly. So if we start with grams, we can get 2 moles by doing some mathematical function. And the same is true if we have moles, we got to go to grams. Looking at the units, we can, we can determine what mathematical function we need to do. And so, for example, if you look at the periodic table for carbon, it has an atomic weight of 12.01. We call that number as a decimal number because that is the average weight of all the isotopes, the weight average of all the isotopes of carbon. Okay, because remember we talked about carbon 12, carbon 13, carbon 11, carbon 14. Those are nice, even whole number weights or AMU units because each proton and neutron had an AMU of 1. So we had nice even numbers, right? But every isotope has a different percentage in nature. So we have to account for the different percentage. And then we average out carbon 11, carbon 12, carbon 13, carbon 14, as per the percentage that they bring into nature. And we end up with this average of 12.01 because the most abundant isotope for the element carbon is carbon 12, okay? And that's why we don't use the atomic weights for determining sig figs because they are the average of whole numbers. And therefore they have an infinite number of significant digits. And to refresh your memory about what we stated with respect to calculations that use the atomic weights we give you in our atomic our periodic table, because there are a lot of atomic weights out there, because like I say, you got an infinite number of decimal places. That could change your answer with respect to Canvas's answer, because Canvas is, in the assignment in Canvas, it's not smart enough. We do our calculations when we make the problems based on the atomic weights of the product table, and then we put those answers on Canvas. And so your number is, even if it's say 12.02, Canvas won't recognize it, okay? Not to say it's wrong, but I'm saying to keep from having me to go give you credit and you get it right, use the atomic weights given to you from the atomic table that we utilize. I will give you credit if you use something else. I just tell you that right now, but this certainly would make things life a little easier. All right. So if you look up sodium from the atomic mass, atomic weight, and let me call up the periodic table here. Our periodic table. You'll see here that every element up here that is not in the parentheses, recall the ones in parentheses are radioactive, and so we really can't get an accurate atomic weight there due to the decomposition of the element. But if we look at carbon, carbon has atomic weight of 12.01, okay? What does that say? That says that if you go to the lab or you weigh out any place 12.01 grams of carbon, guess what? You have 6.02 times 10 to the 23rd atoms of carbon, okay? If you go and you weigh out 10.81 grams of boron, number 5, you have 6.02 times 10 to the 23rd atoms of boron. And that is true for any of these elements, okay? If I weigh out 19 grams of fluorine, which technically wouldn't be correct, right? Because fluorine is diatomic, so actually you double that, okay? So twice that of 19, so would that be 38 grams, right? Because fluorine, chlorine, bromine, iodine, those guys, and oxygen, they are diatomic. But if the question asks you, how many moles do I have in one atom of fluorine, then I would have, if I have 19 grams of fluorine or 1 mole, let me restate that. If I have 19 grams of fluorine, monatomic fluorine, then I have 1 mole, 6.02 times 10 to the 23rd. Okay. But as I stated, fluorine is diatomic, so it's twice this. The atomic weight, molar mass of fluorine would be twice. That'd be 38 grams per mole. So in real life, if I weigh out 38 grams of fluorine gas, I have 1 mole, 6.02 times 10 to the 23rd. And that's true for all of these elements. 63.55 grams of copper, 1 mole. 55.85 grams of copper, 1 mole. Okay. See how that works? If I were to weigh out 2 grams of helium, can anybody tell me how many moles of helium I would have if I weigh out 2 grams of helium? What do you guys think? 2 grams of helium. It's right here. I circled it. If I weigh out 2 grams of helium, how many moles do I have? Well, how many grams would 1 mole of helium weigh? Anybody want to give a shot at that? Let me clear this up here. One mole of helium, how many grams is that?
Four.
You'd be 4, exactly. All right. If I have 1 mole of monatomic nitrogen, how many grams would that be?
14.01.
No. Okay. Monatomic nitrogen, meaning just 1 nitrogen. And if I have 1 gram of that, 1 mole of monatomic nitrogen, how many grams would that weigh? Where's that number
14.
right there? You got it, 14.0. Now, if I would have said nitrogen gas, right? What does that tell you? Nitrogen gas, the term nitrogen gas, that makes it diatomic, right? And 2. So how many grams would 1 mole of nitrogen gas weigh? Any idea? Well, monatomic weighs 14 grams. What would diatomic weigh? Twice that, right? 28 grams. Yeah, exactly, 28.02. Okay. And just like I said, if I need 1 mole of cobalt, How much cobalt would I have to weigh out, measure out in the balance? How much would it weigh? I circled there, number 27, over here. I need 1 mole of cobalt. How much do I need to weigh out? What's that number underneath CO?
58.93.
You're 50 exactly. Okay. Maybe let me try it this way. Let me do the whiteboard. Okay, now I'm going to use an obscure example, but I think this might help. I'm going to use the example of eggs. Okay. Obviously, we know that there are small, and we just say medium and obviously the large. Okay. And let's say I got a dozen of each. All right. And I take that dozen of each part of the eggs and I weigh them. And I'm going to give you an arbitrary value. And let's say for small eggs, they weighed 100 grams per dozen. For medium eggs, we just double it. They weigh 200 grams per dozen. Okay. And the large eggs, they weigh 300 grams per dozen. Okay. Now, can you tell me if I had 2 dozen medium eggs, how much are they going to weigh? I say 1 dozen, I meant 2 dozen. If I got 2 dozen medium eggs, how much are those eggs going to weigh? If I know 1 dozen weighs 200 grams, what would 2 dozen weigh?
200?
No. If 1 dozen, here's this 1 dozen. If 1 dozen weighs 200 grams, how much would 2 dozen weigh?
400?
You got it. 400. All right. If I have 5 dozen medium eggs, how much would those 5 dozen eggs weigh?
10,000?
Not 10. Would it be 10? Or did I do my math wrong? Wouldn't that be 1,000?
1,000.
Yeah. 1,000. All right. And so you see, you're getting the gist here because you know that 1 dozen weighs whatever amount. And if I go even numbers, 1, 2 dozen, I just double, 3 dozen, triple, et cetera, right? Now, let me do something a little bit different. Instead of asking if I start off with 1 dozen, let me ask the question. I need half a dozen. I need half a dozen. If I have half a dozen of, say, medium eggs, how much do they weigh? Here's the question.
100?
You got it. Exactly. Okay, so I know if I go bigger numbers than it does, I just double, triple, quadruple, whatever. But then if I go less, okay, half a dozen, okay, I'm going to have, it's going to weigh half the amount. And if I said 1/4 dozen, how much would 1/4 dozen medium eggs weigh? If half a dozen weighed 100, which you're correct, well, isn't half of 1/2 is 1/4? So wouldn't it be half of that? Wouldn't that be 50 grams? Okay. And let me ask you this. How many eggs is a quarter dozen? How many actual medium? Any dozen. If I have a quarter dozen eggs, how many eggs number-wise does that represent? Or 12 divided by 4.
3.
Exactly. A quarter dozen is only 3 eggs. And those 3 eggs, those 3 eggs weigh 50 grams, all of them together. And they represent a quarter dozen. Okay. So a quarter dozen medium eggs are 3 eggs. In fact, a quarter dozen of medium, small, or large eggs is still 3. Okay. And right now we're using just the term dozen. So what we're going to be doing now is using the term mole, because instead of just 12, now we're going to have a big giant number, 6.02 times 10 to the 23rd. But this concept of a dozen is still the same, whether it be dozen, a dozen equaling 12, or for our case, a mole equaling 6.02 times 10 to the 23rd. Okay. So all of the small eggs weigh 100 grams. Okay. That's like the atomic weight on the periodic table. That is the weight for 1 mole of that particular element. So you don't have to calculate anything. So if you're asked the question, how many moles does how many grams does 1 mole of carbon weigh? Well, you simply go to the periodic table, find the atomic weight, and that is 12.01 grams. Okay, it's like saying how many for 1 dozen small eggs, how much do they weigh? Well, it's 1,000 grams, 100 grams, excuse me. And if I go to another element which is bigger, like copper, what I say was 63. For 1 mole of copper, it weighs 63.53 grams or 55 grams. It's like saying, okay, for 1 dozen medium eggs, how much do they weigh? Well, it's a bigger egg, right? So that's going to weigh 200 grams compared to 100 grams for the small eggs. Because what is the difference between copper and carbon? Well, they got more weight, obviously, right? Because they got more protons and more neutrons. So the weight for 1 mole is going to be bigger. And if I said for even a bigger element, let's pick gold. 1 mole of gold weighs 196.97 grams. Okay, bigger element. Okay, just like saying for 1 dozen large eggs, they're going to weigh more, 300 grams. In both cases, all 3 cases of these egg examples, I have 1 dozen, which is 12. Everybody agree on that? Which is the same thing when I did with carbon, copper, and gold. In all cases, I had 1 mole, which was 6.02 times 10 to the 23rd. They all weigh differently, right? Because they're bigger elements. Carbon is the smallest one, copper is the medium, the next size down, and then gold was the bigger one of the 3. So obviously they're going to weigh more as I go to a bigger element. But what they have in common is that atomic weight. That weight is one chemist's dozen, which happens to be called a mole. Okay. And so let's go back to the periodic table. And let's go back. We talked about carbon right here. Carbon, 1 mole of any of these elements on the periodic table simply weighs whatever their atomic weight is. Why? Because the units for these numbers is grams per mole. Okay? For 1 mole, it weighs whatever its atomic weight is. So carbon weighs 12.01. So if I go out to the lab and I weigh out 12.01, I have exactly 1 mole of carbon atoms, and they weigh 12.01. If I go to the lab again and I weigh out 1 mole of copper, okay, so this is analogous, carbon is analogous to the small example, right? If I go to the copper example and I weigh out 1 mole of copper, I need to weigh out 63.55 grams. Obviously, this is the medium example. It's much bigger than carbon. Why? Because it's got more protons, remember those, and more neutrons. They weigh more, right? And of course, more electrons, but the weight of electrons is minuscule compared to the weight of the protons and the neutrons. And then I went to the example of gold, which is number 79, and 1 mole of gold will weigh out 196.97 grams. Okay, every one of these 3 examples, like they did with the eggs, small, medium, and large, is 1 mole, which happens to be, let me write it here, 6.02 times 10 to the 23rd. The example I did with the eggs, small, medium, large, all what they all had in common was 1 dozen, which means I got a 12 of each, right? The same here, it just put in a bigger number instead of 12. Avogadro's number, 6.02 times 10 to the 23rd. Okay, so going to any element, and the thing that maybe was confusing was the diatomics. Diatomics have no fear of ice cold beverage, right? Those guys are always 2. And so the atomic weight, the molecular weight for them would be twice the single weight. So you got to read the question carefully. Like, for example, if I have 1 mole of monatomic bromine, monoatomic, 1 bromine, then it would weigh 79.90 grams. But if it said, what is the atomic weight or the molecular molar mass of bromine, liquid bromine, because we know it's a liquid. Well, we know that bromine is diatomic, so there'll be twice that, okay? And those are the only ones that you got to be careful. Oxygen will be 32. Oxygen gas, we know is diatomic, so its molar mass would be twice that because it carries 2 oxygens, okay? All right, now, if I weigh out, if I have, who can answer this question? Let me clear this up a little bit. It's analogous to the egg scenario, okay? And I'm still working on carbon. Does everyone agree that 1 mole of carbon is equal to 12.01 grams? Everybody agree on that?
Yeah.
Okay. Also, let's take it further. 6.02 times 10 to the 23rd carbon atoms is equal to 1 mole is equal to 12.01 grams. Okay, everybody agree on that? 6.02 times 10 to the 23rd carbon atoms is equal to 1 mole of carbon, which is equal to 12.01 grams, right? Everybody here on all these elements, every single element here, if I have 1 mole of any of these elements you select, I have 6.02 times 10 to the 23rd. Isn't that the same thing if I said to you, I got a dozen bananas, a dozen oranges, a dozen eggs, a dozen bicycles, a dozen students? What number is it that I have of all those items I just mentioned? And I say it does 12, right? There's no question about that. We understand it doesn't. But where we get into the difficulty is now that number 12 gets changed to a bigger number. And that bigger number is 6.02 times 23rd. Okay, but the concept is the same as the concept of a dozen. It just happens to be a bigger number. All right. If I have 6 grams of carbon, 6 grams of carbon equals how many? Wouldn't that be half a mole? Does everyone agree with that? Remember earlier I said about the medium eggs, they weigh what, 200 grams? If I have 100 grams of the medium eggs, do I not have half a dozen? Okay, well, here's the same scenario. I have half of what 1 mole will weigh of 12.01. I got 6 grams of carbon. Well, that would represent half a mole. Okay, because I'm taking half of 1 mole. You all see that?
Yeah.
Okay, all right, good. So let's move on, because the takeaway from this, besides trying to show you about that big giant number, is that the atomic weights of all these 118 elements have the units of grams per mole. Okay. Or I could say grams per 6.02 times 10 to the 23rd units, or atoms, or whatever element. It could be ions, it could be anything. Okay. These are equal, these ratios. And these ratios can be written either with grams on top and the other number for grams in the denominator. Okay. It is a ratio that we're going to utilize a lot when you get these calculations going here. All right, so let's go back to the chapter. And that's what this page was saying. You're trying to tell you here that 1 mole of any atom by themselves, if either be an atomic, monatomic atom, or the diatomic, it is equal to their atomic weight. If it's diatomic, you just double the atomic weight, okay? And so 1 mole, and let me write it this way. So let's say 1 mole of monoatomic oxygen is equal to 6.02 grams per mole. 1 mole of oxygen gas, which is O2, is equal to 32.000 grams per mole. Okay? And these are for the diatomic scenarios. The diatomic elements. Oops, excuse my writing there. That means that everybody else, whatever element we're dealing with, is simply 1 mole of the atom is equal to its atomic mass, plain and simple. And carbon is 12.01. And obviously sodium, 1 mole of sodium would be 22.99 because sodium is bigger. Sodium has more protons, more neutrons. Its weight's increased, okay? All right. And so if I had 2 moles of carbon, it just double that. Wouldn't that be just 24.02? Sure would. If I had 3 moles of carbon atoms, I just triple it, so on and so forth. Okay. But we're going to use that ratio method to help us out a little better here. Okay, let us continue. All right, so 1 mole, as stated, is 6.02 times 10 to the 23rd entities, units, whatever you want to call it. It's just a number. And these unit entities can be atoms, it could be ions, it could be molecules, or it could be formula units like sodium chloride or aluminum oxide, calcium bromide, etc. Okay. It's a mole of anything. And so we can just go into the periodic table, knowing, keep it in mind that 1 gram, the units for the atomic weights are grams per mole. We can simply go up there and say, for carbon, in 1 mole, there's 12.01 grams. For gold, 196.97 grams per mole, and sodium, 22.99 grams per mole. All of these have 6.02 times 10 to the 23rd atoms, okay? Just like the small, medium egg scenario we did earlier, we had 100 grams, 200 grams, 300 grams per dozen. The common factor they all had was a dozen, same as here, except dozen happens to be a slightly bigger number, okay? All right, now, I mentioned the term molar mass. And what do we do? Actually, what that is, I should have defined it, but we're going to define it now. What to determine the molar mass, it is simply the sum of all the atomic weights of all the elements in the formula. And so here we go. We're going to write the formula property, okay? Like we've been doing. We first break it down into ions, put it together with the correct number of units so that all the positive and negatives cancel out. Once we know which elements are involved here, then we go look up the atomic weights and add up the mass for each of the atoms that contribute to the structure. So the first thing we're going to do is write the formula. So they're asking here, calculate the molar mass. Basically is the total mass per mole for this particular compound. So we have barium, and I've always emphasized what? To write the ions first, right? So we know the hydroxide, hopefully we know that by now, is a polyatomic ion. It's a base, and it has a unit formula of OH negative, okay? Barium is in group 2. So it will have, when it's ionic, a +2 charge, okay? So that means for the formula, I need 2 hydroxides for every barium. So my formula becomes Ba parentheses. I use parentheses because I'm using the polyatomic ion hydroxide, okay? And that is my formula. So writing formulas is very important, correctly, that is, so you can calculate the correct molar mass. All right, so now we can say we got 1 barium, and we have 2 oxygens, and we have 2 hydrogens, okay? Now, once you know the formula and how many atoms each one contributes to the overall formula, you go to the periodic table and you get the barium is 173. So 137, excuse me, 137.33 grams per mole. Oxygen, there are 2 oxygens, and so that's 32.00 grams per mole for the oxygens. Hydrogen, there's 2 hydrogens, each one brings in 1.01. So we got 2.02 grams per mole, okay? And so we tally those values up, and that is the molar mass for barium hydroxide. And let me write this in here. So here's the formula that we came up, and then we add up all the atoms and their atomic mass, okay? And we come up with 171 grams per mole. And that is the molar mass for barium hydroxide. Now, can you tell me how many grams of barium hydroxide do I have to weigh to get 1 mole of barium hydroxide molecules?
Can you ask it again?
Yeah, how many grams do I need of barium hydroxide to give me 1 mole of barium hydroxide? It was just like the previous question when we did carbon. If I weighed out 12.01 grams of carbon, do I not have 1 mole of carbon? And the answer is yes. So here, how many grams of barium hydroxide do I need to weigh out to give me 1 mole? I don't have to calculate anything. It's right there in front of me. Look at my units. I have to weigh out 171.3 grams. Okay, because the total molar mass of barium hydroxide weighs 171.35 grams. The carbon, if you remember, we did carbon, it only weighed 12.01 grams per mole. And so I only needed to weigh out 12.01 grams of carbon to give me 1 mole. Okay, but for barium hydroxide, because it's got more atoms and they're bigger atoms, the total mass for barium hydroxide is 171.35 grams per mole. Okay, this will be analogous to maybe the ostrich eggs, the extra large eggs. They weigh bigger. They're gonna for 1 dozen of those eggs, they're gonna weigh more, right? Okay. And so what do we do here again? To summarize, to determine the molar mass of any formula, okay, we have to first write the formula for any compound. We have to write the formula first, which we did. Given the name, we determined the formula and put everything into ions, right? Put them into ions so you can write the formula properly, correctly with the same number, so the correct number of cations and anions. Once we know that, then we determine how many of each atoms we have. And like I said, we had 1 barium, 2 oxygens, and 2 hydrogens. We go to the periodic table. Barium has 173.33 grams per mole atomic weight. Oxygen is 16, but there's 2 of them, so we got to multiply that by 2. And then hydrogen, so this is oxygen, this is barium, and this is hydrogen. Each hydrogen has an atomic weight of 1.01, but we had 2 of them, okay? And so we tally that up, and that told us, after we did that, that we have for barium hydroxide, its molar mass is 173.35 grams per mole. That is a ratio, ladies and gentlemen. 171.35 grams per mole, or 1 mole per 171.35 grams. Remember when we did 1 inch equal to 2.54 centimeters? Okay, and we wrote that ratio either with centimeters per on top, 1 inch, or 1 inch on top, 2.54 centimeters in the bottom. Okay, remember we did that? Okay, well, we're going to use the same technique here. Once we figure out either the atomic weight or the molar mass, that is nothing more than a ratio that we're going to utilize in our calculations. And we're going to keep track of our units when we start multiplying these factors with some value. And if we set that up properly, our units cancel out. Recall that example of that extreme example I had where I had with dental hygiene students. Remember that example of dental hygiene students and and I forget what it was, 2 precious, I think it was, some crazy conversion factor. I kept track of my units to get me to where I needed to be, okay? We're gonna do the same technique here. All right, so Avogadro's number is a big number, 6.02 times 10 to the 23rd per mole. Therefore, we can write that ratio, another ratio, with the number, the large number in the numerator or the denominator, okay? And it's nothing more, Avogadro's number is nothing more than the unit of a quantity of whatever, it's like a dozen anything. Just happens to be, in our case, Avogadro's number could be atoms, molecules, ions, whatever you're counting. Question here says, all right, we're going to do the same technique we did when we're doing the unit conversion of the English symmetric units. Same process, okay? Keeping track of your units. It looks a little complicated because this obviously is new here, but we're going to break it down and go at it stepwise. Question here says, how many calcium atoms? So we're looking for atoms, okay, are in a quarter mole. That's basically a quarter, 0.25, right? Moles of calcium, all right? And so here in this examples, we are using Avogadro's number, I should say. Either one of these two. Which one we use depends on the units that we need to cancel out. So what is the first thing we always do? We always wrote down what we're given. 0.250 moles of calcium. Obviously, we're going to have a conversion factor here, and we're going to need to get to atoms of calcium. That is what we're searching for with respect to units. Now, since we start off in moles, that means that conversion factor I'm going to use has to have moles in the denominator because I want my moles to cancel. Remember when we did that calculation, how we did those when we did the units conversion factor? Same thing here, okay? Which means that since we're working with Avogadro's number, I need atoms in the numerator, okay? Which tells me I'm using the one on the left because the one on the left up here has moles in the denominator, and that's what I'm setting up. And so now I plug in the numbers that I'm going to use. Check out my units, they cancel out. I got it set up properly. Bang, type it into your calculator. Refresh your memory how to type in scientific notation. You're using either the EXP button or the double E button, or there's a button that is X, then 10 to the X button. Okay, remember we did all that way back then. Go back and refresh your memory which one of these belong to you. It could be a primary button or it could be a secondary button. Depends on your calculator. All right, so I take 0.250 times 6.02 times 10 to the 23rd. Okay, so obviously the number, the number that I'm going to eventually get is going to be much less than 6.02 times 10 to the 23rd because I'm multiplying by 0.25. Isn't that a quarter? I could roughly just, quarter is nothing more than 0.25, right? In decimal form. And so I'm going to have a quarter number of atoms of 6.02. Let me clear this up and show you the number here. And it, sure enough, 1.51 times 10 to the 23rd calcium atoms, okay? So if you had a quarter mole or 0.25 moles of calcium, that represents 1.51 times 10 to the 23rd calcium atoms. All right. Now, Let's break down the second question. Calculate the number of moles. Okay, so obviously way over here, I got equal, and then I need to calculate number of moles with respect to units. And we're talking about oxygen gas. And so O2 here, okay, oxygen gas we know is O2. And they're telling you that if I have 3.75 times 10 to the 27 molecules of oxygen gas, how many moles would that represent? Okay, so we write down what we're given, 3.75 times 10 to 27 molecules of oxygen gas. Oh, let me. Okay, molecules. I'm just going to do shorthand. MOLEC represents molecules of oxygen gas. Obviously, I have my conversion factor. Okay, I want moles in the numerator. Why? Because that's what the question asks for, which means that molecules, MOLEC, would be in the denominator. All right, so guess what? I'm using the one on the right. So 1 divided by 6.02 times 10 to the 23rd. Okay, take my units, molecules cancel, leaving me with units of moles, which is what I'm looking for based on the question asked. And the way I set that up, I know that I'm using the one on the right because I'm following my units, okay? Now it's a matter of you plugging in the number correctly, and you should come up with 6,230 moles of oxygen gas. Okay. Now, let me give you something that will, I don't know, maybe I want you to think about. Okay. Can anybody tell me how many moles are there in, how many grams, number of grams in 1 mole of H2O? How many grams in 1 mole of H2O? What do I need to do first? Don't I need the molar mass of water? Can anybody tell me what the molar mass? I'm going to just label that molar mass of water. Do I not have 2 hydrogens, right? Each one brings in 1.01, so there's a total of 2.02 grams per mole. And then I got 1 oxygen, which I go to the periodic table, and its atomic mass is 16 even, okay? Grams per mole, unit-wise. So the total molar mass of water is 18, oh, you know what, this is 2.02, 18.02 grams per mole, okay? So doesn't that tell you how many grams 1 mole of water would weigh? No? Well, okay, well, let's break it down. We're looking for grams and we need 1 mole. So obviously when I set that up, I need grams over here. And I'm given 1 mole of H2O. And so I'm going to need a conversion factor. And so I want grams in the numerator, moles in the denominator, right? So I did the molar mass, so it's 18 grams, 18.02 in 1 mole. My moles cancel. That means that in 1 mole of water, it weighs 18.02 grams. Okay. Who can tell me how many molecules of water do I have in 1 mole of water?
$18.02.
No. That's how many grams. But how many molecules? How many molecules of H2O in 1 mole of H2O? It's like saying, how many eggs do you have in a dozen eggs? How many eggs would you have in a dozen eggs, regardless of the size? Small, medium, large, or extra large? How many eggs would you have in a dozen?
12.
Exactly. Unless you had a baker's dozen and you got 13, right? Okay. So now, how many molecules do you have in 1 mole? Or I could say, how many eggs do you have in 1 mole of eggs? Or 1 mole of bananas? Or 1 mole of apples? Or 1 mole of students? How many of those items would I have? Avogadro's number? 6.02 times 10 to the 23rd. Okay. Remember that. Avogadro's number is nothing more but a unit. So if I say 1 mole of apples, 1 mole of anything in the world you want to count, you have 6.02 times 10 to the 23rd. No different if I were to say, well, obviously different because the number is different, but analogous to 1 dozen bananas, 1 dozen oranges, 1 dozen molecules of water. You know, 1 dozen is 12. Well, 1 mole is 6.02 times 10 to the 23rd items. Okay. So that is, so for 18 grams of water, I have 1 mole of water, which means I have 6.02 times 23rd molecules of water. Let me clear this up a little bit here. Summarize all this. And so at 18.02 grams of water, H2O, that is equal to 1 mole of H2O, which is equal to 6.02 times 10 to the 23rd molecules of H2O. Okay. Just like we've been doing earlier when we just had an atom, carbon, I got carbon, 12.01 grams of carbon is equal to 1 mole of carbon, which is equal to, guess what? 6.02 times 10 to the 23rd molecules or atoms of carbon, okay? Now, if 18 grams of water gives you that humongous number, I want you to imagine the quantity of water molecules that are in your body. If we had some way of measuring how much water you have, that is a lot of molecules. And then equate that to the amount of molecules in the ocean, how many grams that would consist of. All the water on the earth. Can you imagine how many individual molecules of H2O there exist? It's just a mind-boggling number. And that gives you an indication as to how small these molecules really are. Okay. All right. So right now we started off with moles, but now we're going to do calculating into grams. Okay, grams to moles. We went from moles to molecules here. We started in moles and we actually measured how many or counted how many atoms or molecules we have. Now we're going with grams to moles. So if I start off with X number of grams, how many moles is that consistent of? Okay, just analogous to what we just did with water. If I have 18 grams of water, I got 1 mole. Okay, which if I had 9 grams of water, which is just half of that, I have half a mole. Right? For example, how many grams is 1.667 moles of oxygen gas? Okay, key word, oxygen gas, to trigger that it is diatomic, because we're talking about oxygen gas, or they would have said oxygen atoms, so it's diatomic, which means the molar mass for oxygen gas will be twice that for each individual atom. So that's was 16, right? So it'd be 32 grams per mole. So obviously in each type of calculations, one of the first things you need to do is to identify the molecule you're working with. Okay. And if you don't know the formula, determine the formula. And once you determine the formula, determine the molar mass. Because you're going to need the molar mass in all these types of calculations. Okay. And isn't that related to now kind of tied in a little bit, if you think about it, about these problems we're given? It said, here's the reaction of sodium reacting with chlorine to give you solid sodium chloride. We took the words, converted them into formulas, into reactions and then products, and then we balanced them out. Okay, so this is all tied in. All right, so as always, we write down what we're given, okay, and what we're looking for. And so I'm going to do this one problem, and then we'll stop it here. And so we are given 1.667 moles of oxygen. Okay, obviously I'm going to have a conversion factor here of some sort, and I'm trying to get to grams, so I'm looking for grams of oxygen. Okay, now that means that I need moles in the denominator and I need grams in the numerator. Right, because I want my moles to cancel, and we're talking about O2 here, so I want my moles to cancel. And so my molar mass is 32 grams on the numerator per 1 mole. And I got this from the molar mass of what was given, oxygen gas. Okay, check my units. Units cancel out. Now the math is on you. You're good to go. Plug it in. And you should come up with 53.34 grams of oxygen. Okay. Don't forget your sig figs. You're going to use the moles as your sig figs. The atomic weight, molar mass, we don't use those to determine sig figs. Okay. All right. And we use the moles here given to you to determine sig figs because the moles came from grams, which is a measurement. So that's why this moles is the factor in determining your sig figs. There's 4 sig figs. Your answer should have no more than 4 sig figs. All right. Well, so what does this tell you? That if you weigh out 53.34 grams of oxygen gas, okay, it would correspond to 1.667 moles of oxygen. Okay, And if we needed to calculate moles of oxygen with Avogadro's number, osteo-molecules, I can easily take 1.667 moles of O2. All right, use Avogadro's number, 6.02 times 10 to the 23rd molecules of O2 per 1 mole of O2. And I can actually calculate that. Here, let me do that real quick. 0.667 times 6.02 23rd. And that is 1.00 times 10 to the 24th actual atoms of atoms or molecules of oxygen. Okay, check my math there for you, but to multiply that and I'll give you the actual molecule, just to say. All right. Let's see, there's something else. All right, well, let me stop it here, okay? And we will continue with these problems on Tuesday. And we got